Hi class, welcome again to another session on digital principles and system design. Today we are going to see binary to gray converter, which comes under combinational circuit design. So let us crack on with the lecture. So first of all, if I am given a binary digit, then how do I convert it into gray? Well, my example, let me take, I've got 1001 as a binary number and I need to convert that into gray. So I just take the first most significant bit of my binary number and then, write it as it is in the gray section. Then I add the most significant bit to the next most significant bit, that is the 8 bit and the 4 bit. And then whatever result I get, I just tabulate that in my gray section. Then the 4 bit and the 2 bit of the binary number is added together, and then I get whatever the result I tabulated. And then lastly, the 4 bit and the 2 bit and the 1 bit I added, or the least significant bit is added to the next least significant bit, and then whatever the result I get. So this is how this is how I convert a binary code to a gray. Now, in some scenarios, you might end up with a carry being generated. So in those situations, we just ignore the carry, and then whatever the sum value is, we just take that as the gray code. So now I have a problem. I need to design and implement a 4-bit binary to gray converter. So let me assume that B1, B2, B3, and B4 are the four binary bits, with B1 being the least significant bit and B4 being the most significant bit. So the corresponding gray bits would be G1, G2, G3, and G4. Because if I have 4-bit binary, I'm gonna get 4-bit gray, right? So again, G4 is the most significant gray bit and G1 is the least significant gray bit. So the next step would be to write the truth table. So I have written the binary from 0 to 15 because it's a 4-bit design, right? So I need to write from 0 to 15, and then I have written the corresponding gray bits by the method that I just mentioned earlier in the slide. So from the truth table, it can be observed that G4 is same as B4, which which makes sense because we are taking the first bit as it is, right? The most significant bit is taken as it is. Then G3 is 1 whenever it in the following minterms 4, 5, 6, 7, 8, 9, 10, 11. So if for all these minterms G3 is high, G2 can be defined as sum of minterms of 2, 3, 4, 5, 10, 11, 12, 13. G1 is defined as sum of minterms of 1, 2, 5, 6, 9, 10, 13, and 14. So let us draw a K-map for G3, G2, and G1 and see what is the equivalent reduced Boolean equation for these three outputs. So it is worth noticing that I have taken the horizontal section as B4, B3, the rows as B4, B3, and the columns as B2, B1, because, excuse me, our input is B1, B4 is our most significant bit, and B1 is our least significant bit. So if you're taking 0, 0, 0, 0, then B4, B3 is 0 in the row, and B2, B1 is also 0 in the column. So this way, if I populate my K-map, I can find that there are ones when B4 dash B3 is in the second row, and there are ones in the fourth row. So that comes out to be the simplified version, comes out to be the exclusive OR of B4 and B3. Now here in if I populate the K-map for G2, I find that the simplified K-map is like there are two groups of four, the one in the gray and one in the blue and one in the red. So this when simplified becomes exclusive OR of B2 and B3. And G1 is you've got like two columns that are one, the green one and the red one, and that turns out to be the exclusive OR of B1 and B2. So if I try and realize this as a circuit, then I would require three exclusive OR gates, B4 is same as G4, so I don't need any gate there. B4 and B3 are exclusive OR in order to get G3. B3 and B2 are exclusive OR in order to get G2, and B2 and B1 are exclusive OR in order to get G1. So this is how I realize a circuit, and when I breadboard it or solver it, and I give B4, B3, B2, and B1 as a combination from the truth table, I get the corresponding gray outputs in G4, G3, G2, and G1. It will be interesting to see how this works out practically. I shall see you again in the next session where we shall discuss gray to binary converter. Thank you very much for joining me today. Bye.